Hi everybody. So here we've got a past exam question on integration through substitution and then the volumes of revolution. So this would be part of the Core Pure 2 in Further Maths. I encourage you to give this question a go, where in part A, we need to integrate this using substitution to find the equal to this right hand side. And then for part B, we're going to use part A to help us find the volume of revolution between x equals 0 and pi over 2. You can pause the video, and when you come back, you can check you're working with mine. Okay, so welcome back if you had a go. So we're given this substitution, and we need to use this to evaluate this integral. So the first thing we need to do is we need to work out dx. We find this by differentiating u with respect to x. So this will give us du by dx. When you differentiate with 4x, we get 4. And then we can use the chain rule to differentiate 2 sine 2x. And this will give us 4 cos²x. We can make dx the subject. We'll move that over to the right-hand side and this over to the left-hand side. So dx will be du over 4 plus 4 cos²x. And now we need to change the limits. The pi over 2 and the 0 are both in terms of x, but we need them in terms of u. So if x equals pi over 2, then u, substituting the pi over 2 into here and here, we'll get 4 times pi over 2 will just give us 2 pi. And the sine of pi over 2 is 0, so when you double that, we still get 0. So when x is pi over 2, u will be 2 pi. And when x equals 0, we'll substitute this into u, and we get 4 lots of 0 plus 2 sine 0, so u will equal 0. So we've got dx, we've got our limits in terms of u, now we can substitute u into our integral. We'll have the integral between 2 pi and 0 of e to the u multiplied by cos²x. And then for dx, du over 4 plus 4 cos²x. So what we can do now is we need to work out how this cos²x and this denominator will cancel. Well, the first thing I can do is factor out the 4 from this denominator. Then we can write cos²x in terms of cos². We know cos²x, using the double angle formula, will be cos²x minus sin²x. And we can write sin²x in terms of cos², and then we can expand out this bracket. So we get cos²x is 2 cos²x minus 1. Then we can move a negative 1 over to here, and we'll divide both sides by 2. So we get cos²x is cos²x plus 1 over 2. And then we can substitute this into here, remembering to factor out this 4. And then you can see that because 2x plus 1 here will cancel with this one. So we can simplify this integral. We can also multiply this half by the quarter. So we get the integral of e to the u over 8 integrated with respect to u. And now we can move this 1/8 in front of our integral. So all we need to work out is the integral of e to the u with respect to u. When you integrate e to the u, we get e to the u. So the integral becomes 1/8 of e to the u between 2 pi and 0. Now we'll substitute in the limits. So we'll have e to the 2 pi minus e to the 0, which gives us 1/8 of e to the 2 pi minus 1. And that's what we were asked to show over here. And for part B, we need to revolve this curve 2 pi radians about the x-axis to create the volume of revolution. So if I start a new page, because it's revolved around the x-axis, we know the volume will be pi multiplied by the integral between the limits of 0 and pi over 2 of y² dx. So now we need to work out y². So I'll substitute this for y into the integral, and then we need to square it. So if I work this out separately, we'll square the 6, we'll get 36, we'll square the e to the 2x plus 2 sine x, and using a power rule, this becomes e to the 4x plus 2 sine 2x. And then we'll square the cos x, and we get cos²x. So this is the y². Then I'll substitute that back into the integral here. And now you can see we can pull this 36 in front of the integral. And this is exactly what we had in part A. So we know that when we integrate this between 0 and pi over 2, we get 1/8 of e to the 2 pi minus 1. So I can write this as 36 pi multiplied by what we just worked out. And what we need to do is expand out this bracket, and then we can simplify this fraction so we get our simplified volume here. Okay? Well, thank you for watching, and I hope you found that useful.